Hello, everyone. Welcome to Columbia Astronomy's Public Outreach. This is our first public live stream event, so thanks so much for joining us. My name's Jana Gersovich. I'm the outreach coordinator for the Columbia Astrophysics Laboratory. And we usually do these events live on the Columbia campus and follow them with telescope stargazing. But now we're moving to live stream talks and virtual planetarium events. And we are planning to do more of these in the future. So be sure to subscribe to our YouTube channel and then you'll be notified about our events. We'll also send it out to our normal email list that we use for our in-person events. So in terms of the schedule for this afternoon, we'll start with the talk, which is titled Betelgeuse, 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 the Tumultuous Lives of Massive Stars. And we're going to learn about these mysterious changes that have been observed in a star, Betelgeuse, in the constellation Orion. So the talk will be about a half hour long. Then we'll have some time for chat submitted questions. So feel free to type those into the chat as we go along. You don't have to wait until the end. I'll be collecting them and then we can present them to our speaker. And then finally, we'll do some flying around the galaxy using Planetarium software. So I have some guests with me. We have Micah Achinapura. So say hi, Micah. So he works on planetarium visualization software at the American Museum of Natural History here in New York. And he's going to be acting as our spaceship pilot for our planetarium tour. And I also have with me our speaker, Matteo Cantiello, PhD. So say hi, Matteo.
Hi, everyone.
And he's a theoretical astrophysicist at the Center for Computational Astrophysics here in Manhattan and also at Princeton University. So his work focuses on the life and death of stars. Prior to moving to New York, he worked at the Kavli Institute for Theoretical Physics in Santa Barbara and also at Bonn University in Germany. So thanks so much, Matteo, for joining us today. We're going to take 1 second to switch over to the feed of Matteo's talk slides now. So give us 1 second for that and we'll be right back.
All right. All right. Hello, everyone. Thanks for tuning in today, for joining me for this talk. Yeah, can you hear me? Mm-hmm. Okay, let's see. Okay, cool. All right. Okay, cool. So hello everyone. Thanks for joining me today. And my job today is to tell you a little bit about stars in general, and in particular about massive stars, which turn out to be one of the main topics of my research. Betelgeuse gave me the occasion to bring some interesting aspects of stellar physics and evolution to this talk, because as you well know, Betelgeuse became like a kind of the protagonist of the night sky in the last few months, thanks to his mood swings that led to large variability in its light curve. So it's as you know, it dim its brightness by a substantial amount, and people were wondering what's going to happen next. So we'll get to that. But first, I would like to start talking a little bit about what I'm going to say today. So we'll talk a little bit about the foundation of stellar physics. So what is a star and what makes them shine? These are important questions about the structure and the nature of the energy source that powers stars. Then we'll discuss the fact that stars are not all born equal. They're different, and the way they evolve, they live and die, depends intimately on certain quantities, in particular the amount of mass that they're formed with at the beginning of their life. So we'll go into a story of life and death of stars to get to the point of discussion that is Betelgeuse and try to understand what's going on. Is Betelgeuse about to die and explode as a supernova, or is something different that is happening and it's shaping its surface appearance and the light that it emits? Okay, so what is a star? We're all familiar with stars. We see them during the day and at night. When we look at the night sky, we see thousands of stars with the naked eye. especially if you are in a dark place. Few less in New York City, for example. And when we look at the night sky, we see stars that are mostly, actually, they're only in our own galaxy, the Milky Way. We can see actually the part of the Milky Way in this image. You see as a white stripe crossing the sky. This is actually the projection in the sky of a three-dimensional structure that we're looking inside. It's a disk galaxy, the spiral disk galaxy, with a diameter of about 100,000 light years. So it's a very big structure of gas, stars, and dust. It contains about 300 billion stars, and it's so big that if you are driving a car from one side to the other, it will take you about 2,000 billion years to cross the whole thing, way longer than the age of the universe. So when we're looking at the night sky, actually, we're only looking at with the naked eye, we're only seeing stars that are relatively close, up to a few thousand light years in the neighborhood, so to speak, of the sun. There are stars that are much farther away that we can only observe with telescopes. It turns out Betelgeuse, for example, is one of those nearby stars, so to speak, by being only 640 light years away. Okay, so what we would like to take a little bit of a dive into the Milky Way. I thought about starting with this little video, which it's a nice collage of beautiful images taken by the Hubble Space Telescope. And this will give us a little bit of an excuse to talk about the components of the galaxy. As I mentioned, galaxies, especially all galaxies, but also our own galaxy, the Milky Way, is made of stars, dust, and gas. You can see all those components in this picture here. Let me stop for a second. You can see the stars. You can see the bright gas. Some gas is colorful as well. The red is actually tracing hydrogen in this picture. But also, you can see dark patches of sky, and those regions are not empty. Most of the time, those regions are just occupied by cold dust, and that we'll talk about that later. But in this specific video, we're going to zoom in into a stellar nursery in a region where young stars are formed, and this is called the Eagle Nebula M16. It's a beautiful location full of gas that is currently forming stars. Those pillars that you can see, they're usually described as pillar of creation in this particular image. They're about 400 light years in size. They're 6,000 light years away from us. And these are made of cold, dense gas that is currently collapsing in pockets and forming stars. So it's really like a cradle of stellar life. And we can see actually a bit more. We can zoom in this picture and really check the action of a region where stars are formed. You can see in the top structure, you can see there is a little bit of a star which is emerging out of this cold dust, is blowing out the material from which it's formed from. And how did it form? Well, so the gas was dense and cold enough so that the gravity could take over and keep condensing pockets of this gas. As the gas condenses, its internal temperature increases until at some point the internal pressure of the gas can overcome the gravitational pull. So in a sense, stars are constantly struggling throughout their whole life, balancing two main actions: the force of gravity and the gradient in pressure that is inside their interiors, which produces an outward force. So these two forces have to balance at all time. When they don't, the star contracts or expands. And so you can imagine that to have pressure, you need to heat up the gas. Hot gas have higher pressure. And this heat source have to come from inside the star. And we didn't really know what this heat source that is making stars hot and shine could be until last century, until the 20th century. This is something we learned thanks to the advent of quantum physics, and now we know the reason why stars like the sun, that you can see in this video, do shine this bright. I want to stop for a second and talk about this little video coming from Solar Dynamics Observatory. This is a satellite in space, which is taking light about stars. The first one is that stars are hot. I just said that. You can see it at the surface of the star. The star is boiling. Energy is transported from the interior, where it's mostly produced, to the outer regions. And at the surface, the sun is losing energy in the form of light. Also, the sun, like any other star, is spherically symmetric. This seems like an obvious fact, but it's a direct consequence of the fact that the force of gravity is a central force. That is a complicated way to just say that it only depends on the distance from the center of the object, not from the direction you're approaching the center. And so this gives you a beautifully spherically symmetric shape. I put the Earth in this slide for comparison. You can see the Earth is 100 times smaller than the Sun. I'll give you a little bit of a scale of understanding the differences between a planet in this case, our planet, and a star. So where is this energy coming from? We'll get that to in a second. Something I wanted to say about this picture is also this turbulence that you see at the surface, this complex structure that you see. It's reminiscent of a phenomena that you see every day in your kitchen if you're cooking sometimes, or even boiling water for your tea. This is called convection, and it occurs when you start heating the water from below. At some point, if the gradient temperature between the lower part of your pot and the upper region of the water is large enough, the water starts boiling. So convective motion are transporting part of the energy in a rolling motion of elements of water. This is very similar to what happens in the sun. In fact, those convective patterns that you can see at the surface have really convective cells, like the convective cell you see in the water, with one major difference: their size, their scale. One of these convective cells is as big as California. So this is important to remind, and also something we'll get back when we talk about Betelgeuse, which has even bigger convective cells at the surface. Okay, so but what does make stars shine? What produces the energy that makes the outer region of the sun boil? Well, and also makes it shine. Well, the stars do shine because of thermonuclear fusion. So this is something we learn, as I said, with the advent of quantum physics. We understood that in the very inner region of the star, in the hot, dense core of stars, the temperature is sufficient for a process of nuclear fusion to kick in and produce a lot of energy that can give rise to that gradient pressure that can keep the star in place. So every time they look at the night sky and you see all these thousands of stars, and you know there are hundreds of billions of stars in the galaxy only, you have to imagine that each one of those dots is a self-regulated thermonuclear factory, shining bright because it's making helium out of hydrogen mostly. So most of stars we observe are in that phase of their life. So exactly what's happening is that you have a hydrogen element which is transformed into helium, and this process produces energy. The energy density of this process is so large that it's actually a million times larger than the energy density of typical burning of fossil fuels. So this can provide enough energy for the sun to shine for as long as 10 billion years, which is going to be the lifetime of the sun, our own star. This is great because it provides the constant irradiation and constant temperature at the surface of Earth that let life emerge. If the sun was not living this long, we would probably not have life as we know it. Important point is that nuclear fusion of hydrogen still requires very high temperatures of a million degrees, and needs to be it's naturally confined in the core interior of stars by high pressure loads, something that it's hard to reproduce, at least for now, at the surface of the Earth. Reason why this is not a technology we possess at the moment, but stars do this all the time, no problem. Okay, so because stars burn their interiors inside out in order to stay in a stable equilibrium, they necessarily lose energy. And the reason is that they're hot and they're pretty much in a vacuum, and a hot object in the vacuum irradiates. So that's what makes stars visible. They are visible because they're releasing their energy that they produce through thermonuclear fusion into the universe. This process comes to a cost that they have to burn more fuel as they go. So at some point, the star has to run out of fuel somehow and has to change its structure. This is the reason for stellar evolution, ultimately. The reason why star changes throughout times, and we can talk about the life and death of star. Generally speaking, stars can live for millions to billions of years. The sun, as I mentioned, will live for 10 billion years, which is 5 more billion years. It's about halfway during its process of burning hydrogen into helium in the core. Betelgeuse, for example, which is a more massive star, burns its candle much faster, which means that you only live for a few million years, about 10. Once a star like Betelgeuse gets to the end of its life, something we'll discuss a little bit more in detail later, dies as a supernova. To get there, it has to first go through burning different type of fuels, from hydrogen to helium, helium into carbon and oxygen, and then carbon into neon, neon into oxygen, neon, and then oxygen, and finally silicon, until the core is made only of iron. Once the core is made of iron, no more energy can be extracted through thermonuclear fusion, and a star like Betelgeuse can explode through a process called core collapse supernova. What happens is that the star finally loses that battle I was talking about with gravity, since the pressure gradient is not able to support its structure anymore, and so the star collapses. This collapse ends up in an explosion ultimately that can release a large quantity of material from the star into the space. This is great in a sense because the star, as it was going through its life, the ashes of the production of all the energy required to stay in a stable structure become the ashes that are released into these events that loses mass. And this material can ultimately later on end up in the interstellar medium and later on forms new stars with planets around. And this time, all this material is available for things like biology that we care about. So if you think about everything, most of the stuff you're made of, like the calcium in your bones, the iron in your blood, the oxygen you breathe, the carbon and oxygen and nitrogen in your DNA, all this material was long gone forged inside the hot and dense cores of stars that are no more around. So this is important because it connects the life and death of stars to life and death as we know it on our planet. Okay, so let's start talking a little bit about the details of how stars evolve. As I mentioned, stars are not all born equal. When they're born, they can be born with different amount of mass, different amount of gas, mostly hydrogen and helium, in their interiors. Stars like the sun are very common, and they evolve differently than stars like Betelgeuse. Betelgeuse is a massive star, and I'm gonna show now like a picture of the constellation. That's something we'll maybe we'll look at a bit more in detail later when we fly around in the planetarium. You're all familiar with this constellation. It's one of the, at least I would say, most recognizable constellation together with the Big Dipper in the night sky, at least at our latitudes. And the star Alpha Orion, Betelgeuse, is on the left shoulder of Orion. And it's easily recognizable because of its color. You can see in this picture that it's the reddish, yellowish color in the picture. It's also very bright. And so you can see two main interesting quantities about stars just by this image, but just by looking at the night sky with your naked eye. One thing is that stars have different colors, and this actually turns out to be a measure of their temperature. You know that if you have a flame, the hottest part of the flame is not the red-orange part, it's actually the blue-whitish part. That's the same for stars. The stars like Betelgeuse are red-orange because they're actually cooler compared to other stars that look like blue or white. So Betelgeuse is kind of a cool type of star. It's actually a red supergiant. We'll discuss in a second what that means. And it's also very bright. You can see in the night sky, it's one of the brightest objects we can observe. What that means? Okay, obviously the brightness of a star in the night sky depends on two facts. One is what's the intrinsic brightness of that star. Obviously, if a star is naturally brighter than the other one and it's at the same distance from us, that one will look like brighter. But if that star is also much farther away, then the two factors have to compete. So in terms of to know exactly what's the intrinsic brightness of a star, we need to know its distance and the other way around. So Betelgeuse is this bright and yellow because it's a red supergiant, as I mentioned. It's a red supergiant because it's an evolutionary phase where the star, which was a massive star, increased its radius to about 900 times the radius of the sun. This is showing a comparison between Betelgeuse and the Sun. If you remember, the Sun is 100 times bigger than the Earth. Now Betelgeuse is about 900 times as big as the Sun. And so, what makes stars like the Sun and Jupiter and Betelgeuse different? Well, first of all, stars like the Sun are low mass. So the Sun has, by definition, one solar mass, and it evolves through the main sequence, burning hydrogen, as I mentioned, and then become a red giant. So it increases its radius, and at some point later on starts burning helium in its core. This process can go on until helium is exhausted, and at that point the star is not hot enough in the core to burn any other fuel. The other region of the star actually slowly removed, and ultimately what is left is a white dwarf, which is pretty much the dense hot core of the star. The white dwarf contains pretty much half of the mass of the sun, but constrained into a radius as big as the Earth. So it's a very dense object. For a star which is, let's say, 10 times the mass of the Sun, so 10 solar masses, similar to what the mass of Betelgeuse, the evolution is different. It's much faster on the main sequence. I mentioned that, only 10 or so million years. And then the star, when it runs out of hydrogen in the core, also expands, but this time much more than for the Sun. It becomes what is called a red supergiant. Red supergiants are very interesting beasts, and that's what we're going to focus the rest of our conversation. But as I mentioned, they can go through multiple phases of fuel burning after helium until the core is mostly made of iron. And at that point, the star collapses. You have a core collapse supernova, and what's left behind, it's likely a neutron star. So it's an object with a mass of about one solar mass. But this time is concentrated in the size of just New York City, just 10 kilometers or so. For even more massive stars, which are even more rare, this process can lead to the formation of a black hole instead of a neutron star. But we're not going to talk too much about that. Okay, so if Betelgeuse was going to become a supernova, it would be a pretty interesting sight because it will pretty much look like this. It will be the brightest thing in the night sky together with the full moon. We'll have it lasting for up to a month in this stage, with its luminosity slowly declining. So for a week, we'll battle with the moon for the brightest object in the sky. And so obviously, people were trying to wonder a few months ago what was going on with Betelgeuse, because Betelgeuse was dimming. This is a plot showing as function of time in the period from September to end of January, the luminosity, the brightness of Betelgeuse, and you can see that it was going down quite substantially and quite rapidly. And so the question was, is Betelgeuse maybe about to go supernova? I mean, that was a fair question. And even the Sun talked about the mystery of this dimming star, saying that the famed red supergiant star was getting dimmer, and scientists were very confused about what this could mean. Well, it's partially true. It was not absolutely true. We kind of knew what was going on. A lot of people, I think, chime in on things like Twitter. I did my part. And in the end of December, I think that I was cautioning that all we're saying is like happening in the envelope, not in the core. What I meant is that it's not something that has to do with the fact that the star has run out of fuel and it's about to collapse. It's more something that is happening in the very outer layers that don't really care what's happening in the core, but they only care about details of the processes happening close to the surface of the star. I mentioned pulsation and convection cells. We'll look in a second at what it means, and I caution that very likely will explode, but not anytime soon. Okay, now, Betelgeuse seems to be coming back to normal. As of yesterday, its luminosity is about 90% of its normal value. But, Betelgeuse, this dimming was actually not that exceptional. It was exceptional in the sense that it was happening very fast, and it went down to a pretty low value. But this type of erratic behavior, we've seen it in Betelgeuse for a long time. So this is showing the same light curve, but extended to about 40 years. And you can see that every year or so, with a periodicity of something like a year or so, Betelgeuse is showing large irregular variation of its luminosity. So Betelgeuse is known for being an irregular variable star. So to understand what's actually going on, we have to take a closer look at the star and to the physics of its envelope. So first of all, an important point I want to make is that, remember, Betelgeuse is very large, but just to appreciate how big it is, I actually overplotting it here with the scale of the solar system, and you can see that its size compared with the orbit of Jupiter, meaning that if Betelgeuse was placed at the center of the solar system, Mars, the Earth, Venus, and Mercury will find it themselves inside the star. And the surface will be, and Jupiter will probably grazing the surface of the star. This has an important consequence. If you remember, gravity is a force that depends on the square, on the inverse square law, so inverse square of the distance. That means that something this extended at the surface, the gravity has to be very, very low, even if the mass of the object is larger than the mass of the sun. And so at the surface, the gravity is so low that material is very fluffy and loosely bound, where loosely bound means that it doesn't take much to push it out of the star. The low gravity is also another important consequence. This is another pictorial representation of what Betelgeuse will look like in our solar system. Not good news for us. But if we had a way to look at really from a close distance what the surface of Betelgeuse will look like, this is pretty much what we'll expect. This is a simulation from Andrea Chiavassa and collaborators, and it's a three-dimensional computer simulation of the convective structure of the envelope of Betelgeuse. Again, the sun as a comparison. And remember that the sun has had like 1 million of little tiny cells, tiny but as big as California, at its surface. But for Betelgeuse, the expectation is that we only have a bunch of this cell. And the reason is that the gravity is so low. And gravity dictates the scale of convection in these objects. So we expect this convection to occur on large scales, and also occur fairly slowly on time scale of months to a year, meaning that it will take for a full turnover of the convective blob about a few months to a year of time. So that's the first ingredient. The second interesting thing that is happening in stars like Betelgeuse is that red supergiants are known to be unstable to radial pulsation. This is known both observationally and theoretically. So the reason for this pulsation, which is a radial pulsation, literally the radius of the star is changing at a large, by a large factor, up to a factor of 2 in some cases. This pulsation is due to an intrinsic instability in the outer region that has to do with something called like a opacity-driven engine, which is pretty much like a heat engine. So the large luminosity of the star is cyclically trapped and released by changes in the opacity in the envelope of the star. That the opacity is pretty much a measure of how much the gas interacts with light. And it's produced by changes in the temperature and density of the gas. But temperature and density of the gas change as star contracts and expand. So you can imagine a situation where contracting a star leads to even more trapping of the radiation, and expansion of the star leads to even more trapping of the radiation, which pushes the star to expand even more. So the star is intrinsically unstable or linearly unstable to this pulsation. Now, the important point is that the time scale for this pulsation to occur is very similar to the time scale of a convection to occur. So these two phenomena have necessarily to know about each other and interact. And so we believe that this type of interaction might lead to chaotic variability. You can imagine that once in a while there will be a convective plume which is moving in phase with the pulsation cycle, while other time the opposite. And so in some times you have some amplification of the variability. In other cases, you have some damping of the variability. But is this the whole story? Well, the other very important ingredients that we know play a role in the physics of the other region of the stars is dust. So the image I'm showing here, I want you to have a look, showing the star Betelgeuse as a very tiny dot. So the scale now have changed. Now we're looking at a much bigger region around the star. So the star is that tiny dot at the center inside the black region, and the other red part that you see around are clouds of dust that have been observed using the very large telescope and a camera that is sensitive to infrared emission. And this stardust has been lost in the form of a wind by the star. So what is a wind? Well, a wind is nothing else that a way that the star has to lose material from the surface. If you remember, I told you that the material on the surface is loosely bound, and the star is very luminous. On top of that, the star has this crazy movement going on. So the interplay between this piece of physics lead to the possible ejection of chunks of material from the star. As this material expands and moves away from the star, its temperature goes down, the material cools, the density goes down, and dust can be formed. Once the dust is formed, it absorbs light and then can be visible. So the question is, maybe some of this dust that can be formed in large amount, maybe very close to the star, can also shield part of the star and dim it even further than just the effect of pulsation and convection we're talking about. This idea gained some momentum when we look at the image of Betelgeuse taken by VLT, and you can see here an image taken about a year apart from January 2019 to December, so recently 2019. You can see that the image of Betelgeuse has changed, and a dark area seems to have covered Betelgeuse in the lower right quadrant. And the idea could be, okay, is this dust that just formed close by to the star and is obscuring part of it? So there was even more momentum to this piece of knowledge coming from recent work from Emily Levesque and Phil Massey, colleagues of mine as well, showing large dust grains that might be responsible for part of the dimming. And the way they got to this conclusion is that looking at the temperature of Betelgeuse very carefully. And they figured out that in the last few months, Betelgeuse only changed its temperature by something like 50 degrees Kelvin. This change can only account for about 1/3 of the observed luminosity change, and the rest have to be done by something else. And they, in the spectra, they also see the signature of possible dust, large dust grain formation, which is also observed around other red supergiant stars. So they put everything together and they said, well, yeah, we believe that large dust grains are forming very close and in large amount, larger than usual, close to the surface, and are obscuring for a little bit the surface of the star or part of it, and leading to an extraordinary dimming. Okay, so one question is that we've been talking like Betelgeuse, like this is this crazy, strange star. And in a sense it is, because it's a massive star, and massive stars are fairly rare. They don't live long, and they made in small amounts throughout the universe. But the reality is that actually once a star is in a red, it becomes a red supergiant. Actually, this is a pretty common behavior. They like to do this. The best example I can give you is taking a star that is a red supergiant and is not in our galaxy. It's even in another galaxy, in the Andromeda galaxy, so it's 2.3 million light years away, and showing that on the same time scale as a Betelgeuse is showing very similar type of erratic behavior. So you can see the red dots are showing the red supergiants in Andromeda variability of its light curve as a function of time over 2,000 days, and the green curve is showing some variability of Betelgeuse for about the same amount of time. This is work from Monica Soraizam and collaborators, and there are many other stars like this. I thought about picking like Andromeda because it's so far away. It's so interesting that we can see a star this far, and the only reason why is that red supergiants are very, very bright. Okay, so a little recap before we conclude. So what do we know about Betelgeuse? Okay, Betelgeuse is a massive star. It's about 12 times the mass of the sun. It's past its main sequence, so it's no longer burning hydrogen in its core, as exhausted hydrogen is now burning helium in its core, and it's in the so-called red supergiant phase, which means that it's very extended. It's about 900 times the radius of the sun, and likely burning helium, as I said. It will eventually explode as a core collapse supernova when, as finished burning helium, it will take about 100,000 years. Once you get to burning to helium exhaustion, the subsequent phases of nuclear fusion are very, very rapid. And so it only takes about 1,000 years or less after that point for the star to explode. But the irregular variability that we're seeing has nothing to do with what's going on in the core. We believe it's due to processes that occur in the envelope and above the surface. In particular, convection and pulsation occur in these red supergiants, and they coexist and interplay, and they can lead to kicking material at the surface in certain region more than others, and at certain rate and at some point more than other, such that dust can be formed in different quantities at different time. In particular, the big dimming episode we've seen, it's very likely due to the interplay of convection and pulsation and the formation of a large quantity of large dust grains that are now observed in the spectra of Betelgeuse. So that's all. I wanted to thank you for your attention, and we will now circle back to Jenna so that we can go into Q&A, and later on we'll go flying with the planetarium. This might take a few seconds, but stay on the line.
All right. Well, thank you so much, Matteo. That was a fantastic talk. And we have some questions. And so usually I start out with some of the younger members of the audience. So I happen to know one of our questions comes from a 4-year-old friend.
A certain amount of energy. This energy later on leaks out from the star in the form of photons, meaning like light, and also heats up the gas of the star so that the star can stay in place. So this process can make the star hot for a very long time, compared to a simple process where the star just contracts and heats up by just compressing the gas, where the star will only be hot for a short time, such that we'll not be around talking about it. So all stars are hot because thermonuclear fusion in their cores.
And so for our 4-year-old, it's not like a fire, right? It's like something is changing into another. One type of gas is changing into another type. And you get energy from that.
In fact, people thought initially it was something like a fire. They thought maybe, the sun is made of wood and it's burning. And you can actually calculate, because you know how long it takes for your fireplace to run out of wood. You know how long it takes to burn a log. So you can calculate how many logs you can put in the sun. And if you do that, you figure out that the sun cannot last very long. In fact, can last only for a few thousand years, I believe. I forgot the number, but it's in contradiction with the evidence that shows that the sun has been around for much longer. And in fact, very long so that life could emerge on Earth. We have fossils that show that pretty much, the sun has to be had to be around for at least 5 billion years or so.
Nice. We had another question in that I think you went into this a little bit in your talk, but also what caused Betelgeuse to seem smaller than it actually was? So if you could just summarize again what that difference was.
Yeah. So in fact, what we're seeing is not the size of Jupiter. We're actually measuring its brightness, which it can depend on the size of the star. And as I mentioned, the star is actually pulsating and changing its radial size. But what we believe is the most important factor for this specific dimming was this amount of dust that blocks some of the light. So in a sense, we don't believe that the dimming was mostly caused by changing radius of the star, but mostly by this large amount of dust that block light coming. So I show like this two picture of the radius of the size of the star, and you could see that they're almost like identical, but in one case it kind of looked like it missed a little bit of a corner of the star, and that can be understood by this cloud of material maybe in front of it. So yeah, so it's for this particular event, we don't believe that the radial change was the most important factor.
Mm-hmm. And we had kind of a technical question, which is really interesting, and that is, what do you think of Craig Wheeler's long-standing hypothesis that Betelgeuse once swallowed another star?
Mm-hmm. Yeah. So there's some other. I wanted to generalize a little bit the behavior of Betelgeuse as a prototypical red supergiant. Those red supergiants seem to oscillate, seems to produce dust, seems to have they'll have convection. So all I said kind of applies in general, but Betelgeuse has a few peculiarities that I didn't talk about. In particular, it rotates fairly rapidly for a star at this evolutionary phase. And the reason to understand that it's rotating rapidly is that since it's like a big star, it had to inflate to that point and become red supergiant. And the ballerinas, when they extend their arms, they spin down. So in the same way, a star that size is expected to rotate very slowly. But in fact, Betelgeuse rotates fairly rapidly, almost 25% of its breakup, which is the velocity at which it will start losing material just because it's spinning too fast. And that's a little bit of a mystery. The other thing is that Betelgeuse was likely formed in closer probably to a region of the belt of Orion, but it's actually moving away from that region with some velocity, which is about 20 miles per second. So it's moving very far away. It's kind of slingshot away from that region. We don't know what caused that. One hypothesis is that maybe it was in a multiple system of stars, and there was some dynamic interaction, and maybe two stars merged together, and maybe what we're looking at, it's after a long time, there's still this star that is made of engulfment of two objects, a merger. And it's possible, and I think people are investigating this idea. It's hard to prove it. It's very hard to prove it. And I would say that it might or might not be involved in the current behavior of Betelgeuse. In fact, I believe that probably while it's interesting, it might not be necessarily related to the current behavior. So red supergiants will do this anyway.
Interesting. Yeah, and we had another question about the dimming and possible cause of the dimming. So you talked about the dust, but what about sunspots as a possible contribution to the dimming?
Yeah, so sunspots are caused by magnetic fields at the surface of the sun, and so the process that produces the magnetic fields is called a dynamo, and it produces this ropes of magnetic fields that reach the surface and locally can shut down convection. Now, shut down meaning that if the magnetic field is strong enough, it prevents this blob to move up and down as it should. It provides some kind of it's like putting a rubber band around and preventing things to move. In Betelgeuse, you will need like a large scale field very large scale and large amplitude to, I think, that create like an important effect on the convection that we see. And as far as I know, I believe the effect would not be large enough to create the change in luminosity that we see. Also, it will be hard to, I would say that people haven't explored this idea in depth, but my feeling is that it will be hard to explain the current change in brightness with magnetic fields.
Got it. And one last question before we move on to the planetarium, because I'm interested in it. What might you expect to observe that you would interpret as evidence that Betelgeuse was actually close to going supernova?
Yeah, there will be neutrinos coming. So I think at the distance of, well, we will know the day before or something like that. But at the distance of Betelgeuse, I think you will expect something like 12 hours before to have an increase in neutrinos. The neutrinos, I didn't talk about this, but the reason why stars toward the end of the evolution evolve very fast as they burn carbon and then they burn neon and oxygen and silicon, those phases go very fast. Silicon burning occurs in the matter of a week, which is super fast. And the reason is that, well, not only the star is very bright and you have to supply a lot of luminosity, but most of the luminosity, most of the energy is lost into neutrinos. So the star starts shining mostly in neutrinos, which are particles that we cannot see, but we can detect with some efficiency. And there are instruments on Earth that are built for that. And there's some that can actually will detect those neutrinos about 12 hours before. And there's a ramp up in neutrino emission before the core collapse will be observed. So I think we'll know a little bit before. When we didn't see that in Betelgeuse so far.
Mm-hmm. And what would you do if you saw those neutrinos?
Oh yeah, every telescope in the world would be pointing. I mean, you don't even need certain. I mean, it's a certain telescope. You don't. I mean, Betelgeuse is so bright. I don't even know. I mean, I'm not an observer, but I guess that there will be certain telescopes that we pointed. Certain will be Betelgeuse will be too bright, so we'll have to, I don't know, do something about it. But there will be a lot of frenzies in the astronomical community to get as much data as possible, because there will be a chance of a lifetime. The supernova rate in the galaxy is expected to occur once every 100 years. We are due for one, but we have in modern time we haven't seen one where we had all this instrumentation. So it will be really a fantastic source of information.
Great. All right. So now let's take us to space, Micah.
Awesome. So we'll make us smaller here. And we're looking at Earth.
So Micah, what is this software we're looking at? What is it called? And is this real data?
Yeah, so what we're looking at is called OpenSpace, and it's a free open source piece of software that I am one of the developers of at the Museum of Natural History in New York. And we're working on it in conjunction with University of Utah, NYU, and Linköping University in Sweden. So being that it's a free open source software, we are using all free data as well. So this is a data visualization software, and everything that you're seeing is created based upon a real data point. So the stars are created with a 3D atlas and database of the stars that we have. The image of Earth that you're seeing comes from NASA's VIRRS satellite. And the little orange trail you're seeing of the ISS going around the Earth is data gathered by NORAD tracking objects in the night sky. And so basically we have a data visualization software that combines data from many different sources, bringing it all into one unit.
So that orange is the orbit of the International Space Station.
Yeah, that's exactly right. And so, a lot of people think that's way out in space, but it turns out it's not really that far.
Yeah, so we're actually really close to Earth in astronomical terms, and so the stars that we're going to see in the sky are going to be in the same patterns that we'd observe if we were on the surface of the Earth. And so the constellations, which of course are those patterns of stars that we see in our night sky, are going to be the same from the vantage point here. So we're actually looking out at some of those stars, and we can look around and see if we can maybe find some more familiar ones. So you'll see that stars have different brightnesses. They have different colors. So you're detecting that here. So maybe you have, or maybe you haven't observed stars of different colors, as Matteo was saying, that represents their temperatures. And so our hotter stars are white or blue in color, and our less hot stars are going to be red in color. So you might see a familiar constellation there. So this is, we have Orion on the screen right now. So you can see if you can find the constellation Orion, 3 stars in a row as Orion's belt. And then of course, Betelgeuse is the red star, which is, I guess, the left shoulder as you're looking at Orion. So we're seeing it now. And we could actually put up the lines that connect those stars so that we can actually see the pattern of the constellation. So there we go. So that's Orion in blue. And the stars that are connected. And so this is just how those stars appear from our perspective on or near Earth, right? But the stars that make up constellations, it's just how we see them. So they may or may not be close to each other physically in space. And so something that the software OpenSpace allows us to do is kind of fly out and see how things change so that we can get, instead of one perspective view, we can get a 3D view of these constellations. So keep your eye on Orion here. Yeah, let's zoom out. And you'll start to see these subtly deform and change. And that's the brightness of the sun, which is adjusting so that we can just see things. So that's kind of and there they start to change. You can see some stars are much closer to Earth, which is kind of at the center of where all those lines are pointing. It's lagging a little bit for me. There we go. And so you can kind of see that they're distributed all over the place. So these stars have different intrinsic brightnesses, so the brightness that you'd see if you were near them, but then they're also at vastly different distances. And so those two things combined are affecting how they appear to us.
So let's come back to Earth and then let's go out to Betelgeuse.
Sounds good.
So as we come back, we'll see that the constellations bring the view that we're used to seeing now that we have the perspective from the sun.
So see if you can figure out which one is Betelgeuse now, as things are a little bit distorted and we're a little further out. And then as Orion kind of comes back into shape, you can see if you were right. It's right there. Did I point in the right direction?
So now we're back at Earth, and I'll take us out there. So now as we come out, we can start to see the stars around Betelgeuse. Some are, or the other stars in Orion, some are closer and some are farther away. And now we're approaching Betelgeuse itself. And we can see already that it's larger, it appears larger than some of the other stars around it. So the stars, the size of the dot here will be relative in size of the other stars that are close.
So we can also kind of see all of these constellations in their larger context. because the stars that make up the constellations we see from Earth are actually really nearby to Earth in the context of our larger galaxy. So if we zoom out, we'll start to see our galaxy, which is our local collection of stars and gas, dust, and dark matter. And it's kind of like our larger home. And there you see all of the constellations.
Something important maybe to mention here is that this is really, I like this view because it's showing exactly the point I was trying to make, that all the stars we see in constellation and we see in the night sky, they're very, very local. We think about, looking at the night sky as, looking at the universe, but actually we're only looking at a very, very small patch of our own galaxy. There's so much more out there, so many more stars. And, this is just our galaxy. There are 100 billion of other galaxies out there with 100 billions of stars in each one. So just to put things in perspective, we have a tiny little window on the universe. And it's just with this tiny window, we had so much to learn. So, I usually think about that just to put things in perspective. I feel like this is a good time for that.
Yeah, I actually really like that because even with all the time I've spent visualizing the stars and the galaxy and understanding what proportion of the galaxy these stars take up, I never had actually thought about that in the night sky, we're only seeing stars that are very close to us.
Mm-hmm. Yeah, if you're in a darker location, you might be lucky enough to see those more distant stars. So the more distant stars that are associated with our galaxy, the Milky Way, and they just look like they call it the Milky Way because it kind of looks like spilled milk. It's a diffuse light. It's just kind of, you can't make out those individual stars. They're just too far away. They blend together into just kind of like a soft light that stretches around. And because the galaxy is flat, so we're kind of coming to see the edge of the galaxy here. It's flat like a pancake. We see that diffuse light spread out. It kind of stretches out as a line all the way around our sky as we view it from Earth. Sure. And we had a question whether it's possible to see the Andromeda galaxy with the naked eye in a dark location, and it absolutely is. So Andromeda is a name that we use for a couple different things. So we talk about the Andromeda galaxy, which is a collection of stars, but there's also an Andromeda galaxy, which is a spiral galaxy that is much like the galaxy that the sun is in. So the sun is in the Milky Way galaxy, and then we also have the Andromeda galaxy, which is a similar type spiral galaxy. And you can see it in a dark location in the sky. It's located against that constellation Andromeda, and it appears as a dim patch of light, but it's very small compared to, of course, our own galaxy, which stretches across the whole sky.
Right, so Micah, is the yellow curve like a trajectory of the sun around it? Mm-hmm. So the whole galaxy is moving around with the sun inside and around the center of the galaxy, and that takes about 220 million years for one loop.
Yeah, the galaxy is a young adult. If you're counting, I don't know,
Mm-hmm.
the sun going around is 1 year, which
in galactic years, I like that. Yeah.
mm-hmm. Are those the globular clusters or? Yeah, so these are collections of stars, generally very old stars that formed close to the beginning of the universe. And so all of the more massive stars, so Matteo talked about there being some stars that have a lot of mass and some that have less mass. Those really big stars, they die quickly. And so in these clusters and these groups of stars, all those massive stars have evolved now. And so we don't see them today. We just see those older, smaller, lower mass stars in these clusters. Now, these are just points, but if you were to look at these through a telescope, it would be like a concentration of red stars is what you would observe.
And they are beautifully spherically symmetric, more considering the center, because they had so much time to reassemble into this very specific dynamic configuration. And as you said, all the massive stars that might have been around, they're long, long gone. These things can be as old as billions of years, while massive stars live up to a few tens of million years. So they're all gone. The one we see, they're all relatively young. Like something I like to say is that massive stars, they live fast and die young. They burn a candle very fast. And so, you only see them for a short amount of time and they're gone.
And I wonder if we could, Mike, if we could take one more tour up above the plane of the Milky Way. I just want to look at the different colors in the Milky Way. So we talked about how individual stars have different colors. And you have blue stars, you have red stars, but we also see that stars of different colors, which is most of what you're seeing here that's making up different colors, although there's other things as well that can affect color. But you can see that they're not the same color in every different region of our own Milky Way galaxy. Towards the center, there's redder color to the galaxy, and then in the spiral arms or in the outer layers, you see more blue colors. And so this tells us something about the type of stars that are there and where stars are forming. So when we get new stars, we have some of those really massive blue and white stars included in the collection of stars. We also get the smaller, redder ones, cooler, redder ones. But we get the whole gamut, and those really bright, massive stars make the regions where they're actively forming bluer in color. That's what we see here with the spiral arms.
All right, so maybe I'll take us back to Earth now.
Sounds good.
And we'll take a look at a few stars on our way in. And maybe what I'll do is just to give an idea, we have scaled the stars based on their relative, to give them a brightness similar to you would see when you're at Earth. But maybe just before we go, to show people how many stars are really out here in this database, which is just a small database of 150,000 stars. I'll turn them up a little bit, and it'll appear like I just added a lot more stars onto the screen, when really all I did was increase their brightness. And so if this is just a little spot of 150,000 stars that are near us, maybe it'll start to give people a picture of what's really out there.
Mikey, you're getting a God complex. You're turning all the stars up.
Yeah.
Well, and thanks for the tour. This will have taken 2,000 billion years by far. So we're grateful.
Great. All right. Well, I think we'll come back to Earth, so because we don't want to leave you stranded out in space. So we'll just come in, give you a view of our beautiful planet, and then say goodbye. But before that, I do want to just let you know about some tools that you can use. So skymaps.com is a great place for you to download a map of the sky, how it's going to appear this month for you. No matter where you are in the world, they'll have an option for you. So I'd encourage you to go out and see if you can find different constellations. Orion probably won't be up unless, depending on what time of night you're looking, but you can certainly try to find other constellations, any planets that may be up. And also we have a survey that I'd love it if you guys could fill out. I'm just going to put the URL in the chat here. And it just lets us know a little bit about our audience and help make things smoother for future events. We are planning on having an event next week, so subscribe to our YouTube. You can also go to outreach.astro.columbia.edu and join our email list if you'd like to be emailed about our future events. So thank you so much, Micah and Matteo, and to our whole audience for coming with us today.
Thank you,
All right.
Jenna.
Thanks, everyone.
Thank you, Mika.